graph rational function. Let's say rewrite a rational function of identity and identify the asymptotes. Rewrite g of x for x minus 3. So here they're asking and to write based on the parent function 1 over x to sketch the graph. But let me try with a different approach a little bit. So let me write this function directly to take this asymptote from this function here, horizontal and vertical asymptote, and to sketch this graph to find the x-intercept and y-intercept. Okay, now first of all let me find the vertical asymptote. So the vertical asymptote, we are taking in the expression in the denominator, which is x minus 3. We equate it with 0, and we solve for x. And this implies, so x is equal with 3. So the vertical asymptote x is equal with 3. So we already have this vertical asymptote. And now let's say here is a 3. And let me graph this vertical asymptote. So x is equal to 3. So and let me indicate this one here, a vertical asymptote. So x is equal to 3. And same thing, I am going now to find the horizontal asymptote. Horizontal asymptote, we have some rules that says, for example, if the degree of numerator and leading coefficient, the first term with the leading coefficient here, the first variable, the denominator degree with this degree here in a numerator and denominator, if it's the same, then we have horizontal asymptote, whatever is the leading coefficient here divided by the leading coefficient in the denominator. And this, so according to this one, we already see they have the same degree, the numerator and numerator. Here is a 4, here is 1. 4 divided by 1 is 4. So the asymptote is 4. And what else says is it says, for example, if degree is higher than degree in denominator, then there doesn't exist horizontal asymptote. But if, for example, this degree is 1 less than degree here, then we have the horizontal asymptote that is y equal to 0. So those are some rules. And here, let's say, because it's a 4, I already found the horizontal asymptote. Now let me graph it here, horizontal asymptote. So this is a horizontal asymptote. Y is equal to 4. So let me write HA. So y is equal to 4. And now 3, let me find the x-intercept. So does it have any x-intercept? And to find the x-intercept, first of all, whenever y is going to be equal to 0. So in the same way how we are finding the x-intercept in the quadratic function. So instead of the y, we are plugging 0. And instead of the 4x here, I write the function the way how it is, x minus 3. And now if I multiply whole equation by x minus 3 here, what's going to happen? Let's say here I am multiplying x minus 3 on the numerator. And x minus 3 is going to simplify. But if I multiply this side here, it was 4x. If I multiply the left side by x minus 3 is going to be 0. So 4x from this implies, so 4x is going to be equal to 0. So sometimes when we have this 4, as a shortcut, we just can take a numerator, equate the 0, and we solve for x. And we find the x-intercept. So x is equal to 0. So this is an x-intercept. So here is a 0. But when x is a 0 and y has to be 0 here. And if you're looking, for example, a y-intercept here, because it is in origin, whatever is x and y has to be 0. Same thing. So this is one shortcut how we can verify, how we can find the when, for example, x is equal to 0, y is equal to 0, both of them, they have one of the point in that point are going to have as an intersection. So now x is going to be 0 everywhere, so x is equal to 0 every in this function. So y is going to be equal, we take this original function, 4 times 0 is a 0, so on the top is a 0. And down, what do I have down is x minus 3, so 0 minus 3. So this is equal to 0. So as I said before, so here we have 1 point. Okay. And that's what we found. But just here we have an intercept. In the other side, we don't have any intercept. So, and this is 4. And the 5, if I want, for example, just to make sure what is going on to be the function, here we already see has to go to this point. But because we have an asymptote always has to go, the end behavior of the asymptote is going to be near, and behavior of the graph is going to be near the asymptote. Same thing is going to be in the other side. So the end behavior of the graph is going to go closer and closer to asymptote, so to satisfy those definition of the asymptote. So the side has to go through this point here and has to go through this closer to the asymptote. So we already know this graph has to be in this way. In other words, if you want, for example, to make sure it's going to be positive side here in 0, we can take any number between minus infinity to the 0 and plug here. For example, minus 1 here. 4 times minus 1 is minus 4. And minus 1 minus 4 is a minus. Negative divided by negative is a positive. So it has to be in upper side. But if we want here, for example, we take any number. They take 1, for example. And if you take it, 4 times 1 is 4. And 1 minus 3 is minus 2. 4 minus 2 is minus 2. So it's negative. So the graph is down. So that's what we know. So we need just 1 point to know, and that's enough. And for example, here I have a 3. X is equal to 3. I'm taking any number. Let me take a 4 here. Positive number 4. If I'm plugging here, 4 times 4 is 16. C is, let's say it's 16. And now if I'm taking down, if I'm plugging here, 4 minus 1 is 1. So the number is a 16. It means that the graph has to be in the upper side, in positive. But because, as I said before, this we know the graph of the function, the end behavior is going to be near the asymptote. Same thing happened to be in the other side, near the asymptote. So this is the graph how it's going to have this rational function.